Hi teachers, Eugenio Rivera, Rodrigo Marín, and Sofia Baracat. I'm Jose Vargas, and with my team member, Javier Plaza, sorry, we're going to talk about the importance and presence of dynamics in mining process. Sorry. Right. We have the contents. Talking about the contents, we have different cases of dynamic topics and example for each one. We have three cases. And the conclusion and the literature will help us to research some information about this, every Clil, every case of this. Well, for the introduction, the first that we have to understand is the valuable evolution of mining processes and how that is connected to the importance of dynamics in this. Because the effective analyzing of kinematic, dynamic, and vibration can ensure a good productivity and safety production. Sorry, that happened. Well, for the first case, we have the kinematic of the particle, have a parabolic movement. Then we have these two expressions. And the first of all, we have the x of f equal to x of 0 plus the velocity times time plus the acceleration times time squared divided by 2. And for the second expression, we have the y of f equal y of 0 plus velocity times time plus the acceleration times time squared divided by 2. And for the x of f and y of f have the final position in every axis. For the x of 0 and y of 0 have the initial position of every axis. The velocity of 0 is the initial velocity in each one of the axes of the pen of the equation. T is the time, and A is the acceleration, who can be the gravity, depend of the reference system. Well, in the first case, the key component when analyzing mechanism and machinery is how to simplify them. So for this example, we're going to talk to analyze a rock on a top of a conveyor belt. As we see, the rock can be seen as a particle which moves on a straight line, inclined in an angle of theta. Now, with these following expressions, we can know different variables we can have by these two expressions. First of all, as we say before, the x final equal to the x initial, position initial, plus the velocity in x-axis times time plus the acceleration time squared divided by 2. And for the second, we have the y of final position equal to the y of initial position plus the velocity of y-axis times time minus the gravity time squared divided by 2. We have the difference right here for the another expression. The minus gravity is equal to the gravity in the y-axis. And for the expression to velocity in x and velocity in y, we have the velocity of x is equal to the tangential velocity by the conveyor belt in this axis times the cosine of theta. And we have the velocity of y equal to the velocity of the conveyor belt times sine of theta. Well, for the second case, we have a translation movement and a rotational movement. And we can see this following expression. We have the vector of velocity of b, of the particle b, is equal to the vector of velocity in the particle a, plus the distance between b and a, cross the angular velocity between these two particles, are already said. And we can say this in the light. But, well, for the example of this, we will use this sample, the tunnel boring. Now, for this, in this video, I'm going to show you how's the movement by a tunnel boring. Now we can see this part, this front part of the tunnel boring. We have the carrier head. The carrier head have an angular velocity, angular movement, as we see, and the thrust cylinder, who are these, have a translation movement, who can move forward to the bottom part of the tunnel boring. And this is the two movement of the tunnel boring, right? We can see one more time. And that is, now, for this, we can express these two equations, considering the I before the thrust cylinder, B is after the thrust cylinder, and C is after the carrier head. Now, for the first formula, we have the vector of velocity of the particle B is equal to the vector of velocity of the particle in I plus the distance between B and I cross the angular velocity in between the particle in B and the particle in I. But we can see in this picture, as we can see, between A and B, we don't have an angular velocity. So we can say the angular velocity is 0. And already we can say the vector of velocity in the particle B is equal to the vector of velocity in the particle A. Now for the second expression, we have the vector of velocity of the particle C is equal to the vector of velocity of particle B plus the distance, the vector of distance between the particle C and particle B cross the angular velocity between the particle B and C. As we can see in the photo, that's the place of the carrier head. So we have an angular velocity between these two particles we already defined. Now, for the third case, I'm going to introduce my team member, Javier Plaza.
Hi, I'm Javier Plaza, and I will be continuing with the presentation. Well, we can also analyze a particle with conservation of energy. So we have delta of E, or the mechanical energy, will be equal to 0. E subscript 1 will be equal to E subscript 2. And E1 can be separated into kinetic energy, gravitational potential energy, and elastic potential energy. And this will be equal to the kinetic energy of 2, the gravitational energy of 2, and the elastic potential energy of 2. The example will be the cable drum hoist, which is an elevator used in mining to bring up and down people or material extracted from the mines. In this example, we can use the conservation of energy to analyze between 2 points, which are going to call 1 and 2, described in the picture of the right. So we have the delta of energy, mechanical energy, will be equal to 0. Then E subscript 1 will be equal to E subscript 2. In this case, if we have the system in 2, we are only going to have in 1 the gravitational force. So mass times gravity times height 1, which are m times g times h1, will be equal to 1 divided by 2 times mass times velocity of 2 squared, which are m times b subscript 2 squared. We have mass in each side, so we can extract them and have g times h1 will be equal to 1 divided by 2 times b subscript 2 squared, which are gravity times height in 1 will be equal to a half times the velocity of 2 squared. In summary, we have in Clil 1 analysis of a linear movement of a particle using cinematics of the particle. In Clil 2, we have the kinematic of a particle expressed as a tangential velocity of a particle produced by an angular and a translational velocity. In Clil 3, we have the analysis of a motion of a particle between 2 points using conservation of energy. In conclusion, we have the importance of dynamics in many processes, which are the productivity of the machinery, safety of it, the redesign of the mechanism of machinery, or the optimization. So with the dynamic, we have so much to work with, and we can improve the mechanism and machinery using different materials, shapes, or using different applications for it. This is the literature for the presentation. We have the friction hoisting in North America, the innovative main hoist from FLS, the exploring TBS method of tunneling, and the editors of Encyclopedia Britannica. Thank you so much for listening.